Okay, so for the fourth section in chapter 12, the learning objectives will be to learn to draw structural constitutional isomers, condensed isomers, and line formulas for simple chemical compounds. We are going to convert any structural, condensed, or line formula into its alternative. So, first of all, the structural formulas. Structural formulas illustrate the connection of every atom and their bonds. So, with butane, butane has 4 carbons that make up the backbone. In order for carbon to exist, it needs to have 4 bonds. So that helps us figure out where all of the hydrogens are distributed. This is a structural formula for butane. Another isomer of butane, which by the way, its formula is C4H10, is going to be 2-methyl propane. Being propane, it's going to have a 3-carbon chain, but on the middle carbon, we're going to have another carbon. Now we can fill in our hydrogens based off of the fact that every carbon must have 4 bonds. And this would be the structural formula for 2-methyl propane. Basically, what I want you to note here is I want you to understand that I have illustrated the connection of every atom. I have shown you where the carbons are, I have shown you where the hydrogens are, and I have shown you the type of bond that exists between that carbon and hydrogen. The second type of formula that we will be working with is called a condensed formula. This is a shorthand notation of drawing structures in which the carbon-carbon bonds and the carbon-hydrogen bonds are simply understood rather than shown in the backbone of the compound. The only bonds we actually show in a condensed formula will be bonds to branches, or if we do have a functional group present, it will be the bonds to the functional group. But in a condensed formula, what we're going to do is we're not going to show the bonds for every single carbon-hydrogen bond. They are understood. So let me just illustrate what I mean. So let's take this butane that we just worked with. This first carbon has 3 hydrogens attached to it. So we would write CH3. The next carbon has 2 hydrogens attached to it. So we would write CH2. The next carbon has 2 hydrogens attached to it. So we would write that as CH2. And the last one has 3 hydrogens attached to it. And so we would write it as CH3. This would be the condensed formula for butane. I am basically telling you that on the first carbon, there are 3 hydrogens. And then we go into that carbon-carbon backbone. And on the next carbon, there are 2 hydrogens. But the difference is I'm not showing you the connections. I'm simply indicating that they're there. Let's look at the 2-methyl propane and do the same type of thing with it. So let's begin with the far left-hand side with the CH3. The next one, this is where it's a little bit different. The next one is going to be simply a CH group. But attached to that CH group is a CH3 group. And then finally, we finish off with another CH3 group in the backbone. So what you will notice is that the backbone simply is stating the number of hydrogens on each carbon, but the bonding is assumed. The only bond I am actually illustrating is the branch that is being shown. Now, we can occasionally take a condensed structure and simplify it further by taking out all the CH2 groups and writing them in parentheses with the number of CH2 groups as a subscript to the right. So let's just take butane. So what we would do with butane is we would start out with our CH3, just as we already have in the condensed formula. But then we would notice that the next two were CH2 groups. Whoops, I accidentally hit the wrong thing. The next two were CH2 groups. Instead of writing those individually, we can take and condense that so that the CH2s are placed in parentheses with the quantity of CH2s listed next. And then we would have to finally finish it off with the other CH3. And so that would be butane. Now, butane, it's not that much of a savings. But when you start getting into something like hexane, you can quickly see where the savings comes into play. So the the condensed formula for hexane is CH3, CH2, 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 CH3. We can take this middle portion and we can condense it so that we write it as CH3, and then there are 4 of these CH2s that go back to back, followed by a CH3. And so this would be the condensed or the further condensed structure for this long chain alkane. Now, I will use the structural formulas on occasion. I will use the condensed formulas on occasion. But the simplest way to write a compound is using a line structure or line angle structure. This is a shorthand notation where the carbons and hydrogens are not explicitly shown. Instead, they are understood. A carbon is understood to be at any point where a line begins or ends, and at every intersection of 2 lines. And hydrogens are understood to be wherever they are needed to be in order to give the carbon 4 bonds. The only thing we will show in a line structure are elements that are not carbon and hydrogen. So let's just look at an example here. Let's go with this butane that we've been working with, and let's look at the line structure. So butane has 4 carbons. So basically, it's got to be at 4 points. So you have point 1, 2, 3, 4. That is the line structure for butane. And basically, without illustrating, there's a carbon at each of these points along the line, kind of like a constellation, but we don't show those points. And we know the number of hydrogens based off of the fact that carbon must have 4 bonds. So, for example, this very first one here, there is only 1 bond showing. Because there's only 1 bond showing, that must mean that this particular carbon has 3 hydrogens attached. The next one in line has 2 bonds showing on it. And so in order to get to 4, we would need 2 additional bonds. So this one must have 2 hydrogens, even though they're not shown. And so that's how you work through it. So with this 2-methylpropane, if you go back up, you'll find the structure. It had a propane backbone that had 3 carbons. So 1, 2, 3. And then off of the second carbon was another methane group. So this is actually the line structure for 2-methylpropane. And again, we can figure out the number of hydrogens because of the number of bonds needed to get to 4. Hexane, if you look back, it was 6 of them. So 1, 2, 3, 4, 5, 6. That is the line structure for the straight alkane chain of hexane. Now, ethanol, if you'll recall, the all means an alcohol, which means it's going to have an OH group attached to it. We have to illustrate the OH group because we have to illustrate the functional group. But ethanol means that there was only 2 carbons. So it's 2 carbons, 1, 2, and then that carbon's attached to an alcohol functional group. And so this would be the line structure for ethanol. Propene. Propene, if you go back when we were talking about alkenes, was a 3-carbon chain, but on one of the carbons, it had a double bond. So we would illustrate that double bond as a double line. And so this would be the line structure for propene. You need to become familiar with these line structures because while for small molecules, writing out the structural and condensed formula is easy enough. When you start getting into the larger molecules, it becomes very tedious to write out the structural or condensed formulas. So being able to write out the line formula will save you a lot of time in the end.